Light diffracted from a point passes through the Fourier plane to form diffraction patterns. Undiffracted direct light or zero-order light falls to the centre as a bright spot. Usually, in symmetric illumination, the pattern forms with a mirror image in the opposite half of the circle. Therefore, if the right half of the Fourier plane is blocked by a semicircular half-stop, there is still sufficient information remaining to form a complete image, and also the contrast becomes enhanced as explained below. In some methods, transparent specimens can be imaged because the diffraction pattern contains information about how much light is slowed as it passes through parts of the object, due to the fact that the refractive index of the object differs from its surroundings. Where phase varies across the object, the gradient or slope of optical path difference can be increasing or decreasing or constant, usually with the appearance of an undulating landscape. Light passing through a region of increasing or positive gradient is bent to the right, and negative gradients bend light to the left. Consequently, where a half-stop is used to block the left half, positive gradients appear brighter and negative gradients appear darker. This is the basis of all asymmetric methods, including oblique microscopy and Schlieren methods such as SSEE. It causes a type of shadowed relief contrast that cannot be seen in ordinary bright field. These diagrams represent the effects of masking out either the centre or the periphery of the Fourier plane. We have an etching of Mr. Fourier and his coat that loses all fine detail in one case and shows only edges and fine detail in the high-pass filter images. In some cases, it may be desirable to use a partially transmitting filter to alter the relative weighting of the spatial frequencies. Brett Schneider and Tunis recommended a similar type of apodizing strip along the straight edge of the CAF half-stop. This diagram shows a simple patch stop oblique method that gives strong contrast. The right panel shows the positions in the Fourier plane of zero-order light and several diffracted orders. Normally, in symmetrically illuminated bright field, the zero order falls in the centre, and a nominal 1 or perhaps 2 orders fall inside the aperture, while the higher orders must fall outside. This limits the image resolution. In the oblique method, the zero order falls near to the edge of the aperture, while some of the third and fourth order light can enter the objective and improve the theoretical resolution by up to 100% in one direction, with a reduction of 50% in the perpendicular direction. Hoffman modulation contrast is also related to the Schlieren methods. Hoffman uses unilateral oblique illumination through a slit in the periphery of a condenser mask. A special modulation system in the conjugate Fourier plane rejects light from the left sideband while attenuating the slit of direct light. The right sideband passes freely into the aperture. A further refinement uses a rotatable polarizer in the illumination path, coupled with a small fixed analyzer to adjust the direct light intensity. Some of you may be familiar with the ultramicroscope invented by Seidentopf and Sigmoidi in 1903. It uses a very low NA horizontal illumination to give dark field images. It was used for highly diluted colloids of gold particles in water or sometimes in glass. It detects particles but does not properly resolve their detail. For submicroscopic particles, an airy disk or point spread function is observed. The particles must be diluted enough to stand alone in the field. If a neighbouring particle is closer than the limit given by the Rayleigh criteria, the particles become merged in the image. Note that some of the lower order light is closer to the horizontal, so in this method it does not enter the vertical objective. One historical fact that most people have forgotten is another Seidentopf invention in the same year, now called the coaxial dark-field microscope. It has a similar low NA condenser, but it's in the usual axial orientation instead of horizontal. A spot of paint is carefully applied to a ground-off spot in the centre of a curved oil immersion objective, and this acts as a high-pass filter. It has much the same function as an axial Fourier stop, that is, to block zero-order light. Seidentopf commented that he was unable to detect tiny biological particles using the horizontal method discussed above, and this is probably because biological particles scatter less light than gold particles. He had some success using the coaxial dark-field method with the biological specimens, probably because he could capture the low spatial frequencies, which tend to be much brighter than the higher order light. If he did not remove the zero-order light, the dark-field image components would be overwhelmed by white background and contrast would be completely lost.